So to understand diffraction more intuitively, we begin with the famous Bragg Law. Imagine a crystal as a stack of parallel atomic planes separated by a distance d, as shown in this figure. An incoming X-ray beam strikes these planes at an angle θ1, which is called the grazing angle measured from the HKL plane as shown. Some of the radiation is scattered or reflected by atoms in each plane. So here we consider the simplest interference between two X-rays reflected or scattered specularly from adjacent lattice planes. By assuming specular reflection here, we mean the grazing angle θ1 is equal to the grazing angle θ2. And also the second assumption is the so-called elastic scattering, where the outgoing X-rays have the same energy as the incoming X-rays. So the magnitude of the wave vector is a constant, indicating that the wavelength is not changed after the reflection. Now consider two rays, one scattered from the upper plane at the grazing angle θ2, where we know now θ1 equals θ2, and we call it theta. Another scattered from the adjacent plane below it at the same grazing angle theta. The second ray travels a slightly longer distance as shown here, and we know that the extra path length turns out to be equal to 2d sine theta. So please note that two important assumptions are made in this model. The first assumption is specular reflection, meaning the incident angle equals the reflection angle. And the second assumption is elastic scattering, meaning the magnitude of the wave vector remains unchanged. Okay, so in reality, diffraction of X-rays by crystals was first discovered in 1912 by Max von Laue, a German physicist who won the Nobel Prize in Physics in 1914. Also in 1912, William Lawrence Bragg discovered the law to calculate the positions of atoms in a crystal from the way the X-ray beam is diffracted. He and his father, Sir William Henry Bragg, later shared a Nobel Prize in 1915 for their services in the analysis of crystal structure by means of X-rays. Okay, we just showed that under the assumptions of specular reflection and elastic scattering, the path difference of the incident and reflected X-rays from adjacent lattice planes is equal to 2d sine theta, where d is the interplanar spacing between adjacent lattice planes and theta is the grazing angle of the incoming and outgoing X-rays. Now, if the path difference is equal to an integral multiple of the free space wavelength of the X-ray, meaning that at the same position along the direction of propagation, the reflected beams or waves from adjacent parallel lattice planes are in phase, then constructive interference will occur. On the contrary, when the reflected X-rays from adjacent parallel lattice planes are out of phase by 180 degrees, we have totally destructive interference because their amplitudes add up to 0. This is the case shown in the figure on the right. Because the interplanar spacing d is fixed for a family of lattice planes, only certain values of theta can produce constructive interference from one family of lattice planes. So this condition, 2D sine theta equals n lambda naught, ensures that all scattered waves add together in phase. If this condition is not satisfied, the waves interfere destructively and the intensity becomes very small. One point that is worth mentioning here is the grazing angle. It is conventionally used in X-ray diffraction because the incident beam is generally fixed in direction, making 2 theta, which is the angle between incident and reflected waves or beams, one of the easiest to measure. Another important point is that diffraction peaks occur only when the wavelength is comparable to the lattice spacing. In fact, the condition lambda naught must be smaller than 2D must hold for diffraction to occur. This explains why X-rays are ideal for studying crystals, because typical atomic spacings are on the order of a few angstroms, which matches X-ray wavelengths very well. Now that we have introduced the Bragg law, let's take a look at the image shown here. This image shows the X-ray diffraction patterns of polycrystalline and single crystal chromium oxide. To understand this image, we need to go through some background knowledge. In X-ray diffraction, in general, each plane reflects only an infinitesimal fraction of the radiation, and the X-ray penetrates very deeply into the crystal, so that 10 to the plus 3 to 10 to the plus 5 of layers contribute to the diffracted intensity, resulting in very sharp maximum or bright spots, as shown in the image on the right. In the far field diffraction pattern of a crystalline material. However, in a polycrystalline chromium oxide, the periodicity exists only in a short range, and there exist regions of different periods and orientations of the lattices. Instead of showing bright spots as in the crystalline case, the far field diffraction patterns become a set of concentric sharp rings, as shown on the left. Next, it is worth mentioning that although the Bragg law is extremely useful, it is actually a simplified picture of X-ray diffraction. In the Bragg model, the crystal is treated as if it were composed of flat lattice planes. At first glance, this doesn't make a whole lot of sense. It has very little physical justification because the crystal lattice planes are certainly not flat for X-rays that have a wavelength similar to the atomic spacing. For example, the atomic radius of a silicon atom is 111 picometer, while the typical wavelength range used in X-ray diffraction for crystal structure determination is approximately 0.5 to 2.5 angstroms, equivalent to 0.05 to 0.25 nanometers. So in reality, X-rays scatter from individual atoms. The electron density distribution also plays a role, and basis atoms within a unit cell can modify the diffraction intensity. Because of these complexities, the Bragg law is not easily generalized to include atomic basis structures, electron density distributions, and complex unit cells. Nevertheless, the Bragg law works remarkably well in practice. So later we will see that Bragg law actually emerges as a special case of a more general theory known as the law description of X-ray diffraction, or law formulation of diffraction.